In this video, we continue our discussion of affine varieties with a lemma about finite unions and intersections of affine varieties. So here's a fact. Turns out that if you have two affine varieties, the unions of those, or the union of those affine varieties is also an affine variety, and the intersection of those affine varieties is an affine variety. And of course, if you can do that once, then you can do that, as many times as you want. So finite unions and intersections, that's unions and intersections of a finite number of affine varieties, will give us other affine varieties. So here's our lemma. It says that if V and W are in subsets of n-dimensional affine space, where we have a field K, and they're both affine varieties, then the union of V and W and the intersection of V and W are affine varieties. And then in the proof in the book Ideals, Varieties, and Algorithms by Cox, Little, and O'Shea, they actually specify what those intersections and unions would be. This is pretty straightforward. This one just says that the intersection of V and W is just the affine variety defined by all of the equations for V and all of the equations for W, or excuse me, all the polynomials that define V and all of the polynomials that define W. And then this just says that if you're talking about the union of those, well, it turns out that the union is given by this. Basically, you take a product of each of the equations for V, and you take each of those equations for V and you multiply them by the equations for W. And then, so if you've got S equations over here and T equations over here, you're going to have S times T equations that define the union of the two affine varieties. So let's prove this by assuming that V is defined by the polynomials f sub 1 through f sub s, and W is defined by the polynomials g sub 1 through g sub t. And we'll do the first one first. It's pretty simple. And whenever we're doing a proof of something like this, we get to assume this beginning part. It says, if this is true, then this is true. And specifically, we want to say that if this is true, then this is true. And if this is true, then this is true. So we need to assume that V and W are affine varieties in n-dimensional affine space. And we're going to choose them to be defined by f sub 1 through f sub s and g sub 1 through g sub t. And then our goal is to start with only that assumption and what we know about affine varieties, and use that to show that the intersection of V with W is this affine variety. This is a direct proof. If you've ever taken a theorem proving class, you're just going to assume P is true, and you're going to try to show that Q is true. Just trying to show that P implies Q. Okay, so first we're assuming that V is the variety defined by these polynomial functions, and W is the variety defined by those polynomial functions. And the solutions are an n-dimensional affine space. So that means that these functions, f sub 1 through f sub s and g sub 1 through g sub t, are all functions of n variables, which we'll call x sub 1 through x sub n, because the solution sets are in n-dimensional affine space. So V is going to be the set of all points A, which we can think of as ordered n-tuples in affine space. I'm just going to start using A instead of writing out that n-tuple every time, such that f sub I of A is equal to 0 for I equals 1 through S, and W is the set of all points A in n-dimensional affine space. So these are ordered n-tuples. such that those functions g evaluated at a are all equal to 0 for j equals 1 through t. Okay, now we want to look at points in the intersection of v and w. Now, hopefully you remember what intersection means. This is the set of all points A in n-dimensional affine space such that A is in the set V and A is in the set W. That's just the definition of an intersection of two sets. If you've taken pre-calculus, you've got an interval from here to here and an interval from here to here. If you're looking for the intersection, you're looking for the x values or the t values where those two overlap. The intersection would be here because you'd be looking for all the numbers that belong to this set and this set. And that would be the numbers in this set. We're talking about the same thing here, it just looks a little bit more abstract. So we've got the intersection of V with W is all the points A in n-dimensional affine space such that A is in V and A is in W. Well, if A is in V, that means that f sub I of A is equal to 0 for all, for I equals 1 through S. And since A is in W, G of, or G sub J of A is equal to 0 for J equals 1 through T. So this is the set of all points A such that these are all 0 and these are all 0. Well, that's by definition this variety. So this intersection of V with W is the variety defined by the polynomials that define V and the polynomials that define W. So if we're in this set, that means that we're in this set and this set, which means these are all 0 and these are all 0. And if both of those are 0, then we're saying we're in this variety as well. So that proves this, that if these are affine varieties in n-dimensional affine space and we're defining them this way, the intersection is that. This one is a little bit trickier. So we want to show the following. So we want to show that the union of V with W is equal to this product, or the variety defined by these products. You take the polynomials that define V and the polynomials that define W and you multiply them together. And those are going to be the equations that define, or the polynomial equations that define the new variety. Oops. Over here. In order to show that, basically we want to show that this set is included in this set, and we want to show that this set is included in this set. So our approach is to show that if a number A in n-dimensional affine space belongs to this union of V with W, then it has to belong to this set over here. And I'm just going to abbreviate that this way, but you know that those are the restrictions on I and J. If we can show that every element in this set is also in this set and every element in this set is also in this set, well, if these guys are all included in this guy and these guys are all included in this guy, all of these points are in this set and all of these points are in this set, well, then they must be equal to each other. So we're going to show that this is true, and we're going to show that that is true. So that just requires starting with a point in this union and then showing that if A is in this union, so if A is a solution, well, if A belongs to this set, then A must be an element of this set. And then we're going to say that if A is an element of this set, then A must be in that set. And A is a point in n-dimensional affine space. So we're still making the same assumptions about the structure of V and W. V is in n-dimensional affine space, and it's defined by the polynomials f sub 1 through f sub s, and W is defined by the polynomials g sub 1 through g sub t. And now we want to start with a point in the union of V and W. So we're going to say let A be an element of V union W. Well, just by the definition of a union, then that means A is either in V or in W. It's one of those. You can think of this, if you've taken pre-calculus, as you're looking for all the elements that belong to this set and to this set. The intersection is the points that they have in common. The union is the set of points that belong to this set or both. So in this case, our union would be this. Same idea here, but it's just a little bit more abstract. And A is a point in n-dimensional affine space. Okay. So we start with this. And since A can be in V or in W, we can just pick one. So let's just assume that A is in V, just to have one to start with. Then we know that f sub I of A is equal to 0 for I equals 1 through S, because that's what it means for A to be a member of this affine variety. That means that all of the equations or all the polynomials that define the variety V are equal to 0 at that point. Now, if all of those equations are equal to 0 at that point, well, then we're guaranteed that when I take that point and I substitute it into f sub I times g sub j for I equals 1 through s and j equals 1 through t, well, those products are going to be equal to 0 as well. So if A is in V, then this is equal, or then the f's are all equal to 0. And since the f's are all equal to 0, we take that f sub I of A and we multiply by g sub j of A, we're definitely going to get 0 for I equals 1 through s and j equals 1 through t. Because we've got a product, we've got something that's equal to 0 and something that may or may not be 0, but when you multiply them together, you're definitely going to get 0. Since this is going to be true for all of the equations that define this variety, then A belongs to this variety given by a product of those two polynomials, f sub I times g sub j. So what we've shown there is that V is a subset of this variety defined by this product. Well, we could have just as easily assumed that A was an element of W. So if A is an element of W, then the G sub J of A, those are all going to be equal to 0 for I, or for J equals 1 through T, which means that the products will equal 0 for the appropriate restrictions on I and J. which means that yes, that means that A is an element of this set, and if A is an element of that set, starting in W means that you're an element of this set. So now we have shown that W is a subset of this. Oops, this should be a product. So now we've shown that if A is an element of V, it belongs to this set, or if A is an element of W, it belongs to this set. So putting those two pieces together, that means if A is an element of the union, then A is an element of that set. So that just means that this union is a subset of this guy over here. Okay, so that means if we have a point that belongs to this union, then we definitely have that, or then that point A also belongs to this set. Now we want to show that it also goes the other way, that any member of this set has to belong to the union. Okay, so now we want to assume that we're in this set and then show that if we are in this set, we have to be in this set. Now remember, this is a subset of n-dimensional affine space. So when we say that A is an element of this set, we're saying that these products are all equal to 0 for I equals 1 through S and J equals 1 through T in n-dimensional affine space. But since these are points in n-dimensional affine space, we know that either A is going to lie in V or it's not going to lie in V. So we can say that since A is an element of this set, because it has to be an element of this set because it's an element of this set, then A is either in V or A is not in V. It's got to be one of those. So let's assume for a second that A is in V. So split this into cases. Well, if A is in V, then A is obviously in the union of V and W. And that means that if A is in this set and A is in V, well then this set is a subset of this set. You might be saying, is that even legal? It is, because we're just thinking about all the possible points that are in n-dimensional affine space. Okay, now let's assume that it's not in V, okay? So it was either gonna be the case that A was in V or not. If A is in V, then this inclusion holds. Now let's say it's not in V. Okay, so if A is not in V, well, that means there's at least one function. So there exists one function. Let's call it f sub I naught, because that's what they call it in the book, such that f sub I naught of A is not equal to 0. And this is where I naught is on the list between 1 and S. So basically we're saying there's got to be some function in that defining list of polynomial functions for the affine variety V where that polynomial is not equal to 0 for that value of A. Say, okay, but remember our initial assumption, we've already assumed that this is true for this part. We're assuming that A belongs to this set, and we're assuming that A is not an element of V. So since A is not an element of V, we know that this is true. since A is an element of this set, we know that all of these products have to be 0 for I equals 1 through S and J equals 1 through T. Oops. So this means that when G is equal, or when J is equal to 1, let's say, and we take those products and we evaluate them at A, we have F sub 1 of A times G sub 1 of A, and that's equal to 0. And F sub 2 times G sub 1 of A is also equal to 0. And F sub 3 times G sub 1 of A is equal to 0. And this is true all the way through F sub S times G sub 1 of A is equal to 0. And that's for J equals 1. And this continues to hold for J equals 2 and J equals 3 and J equals 4 all the way through J equals T. So eventually we're going to have F sub 1 of A times G sub T of A is equal to 0, and F sub 2 of A times G sub T of A is equal to 0, and F sub S of A times G sub T of A is equal to 0. So this is I equals 1 through T. We're going to have all of these equal to 0. But remember, what we're saying is that there is some function on this list from F sub 1 through F sub S for which we don't get 0. So if we're talking about that particular value of I naught, that particular value on this list from 1 through S, well, we're going to have T equations associated with that I naught. We're going to have F sub 1 of I naught times G sub J, where J goes from 1 through T, and all of that has to be equal to 0. But F of I naught of A is not equal to 0. I hope you see where I'm going with this. So you have F sub I naught of A times G sub J of A. That has to equal 0 for J equals 1 through T. And we already know that F sub I naught of A is equal to 0, or is not equal to 0, right? Because we have assumed that A is not an element of V, and if A is not an element of V, that there must be one of the polynomial equations that define V for which we don't get 0 when we plug in A. So at that particular value of A, we have, or at that particular function on that list, when we evaluate this product, we're still getting 0 for J equals 1 through T. Well, if this is non-zero, that means that the G sub J of A are all 0 for J equals 1 through T. And that is the definition of being in the set W, because that means A satisfies all of the equations for W. So what we've just shown is that if A belongs to this affine variety and A is not in V, well then A has to be in W. So that means since A is in W, A is definitely in this union of W and V, because that's the definition of a union. So that means in that case, this set is a subset of the union of V and W. So we've shown that if we belong to this set and A is in V, well then this inclusion holds. And then we said if A is not in V, well then if A is not in V, then it turns out that A is in W, so this inclusion holds. So we've talked about all the possible cases. A either was in V or it was not in V, which meant that A was either in V or in W. So we're saying that if A belongs to this set, then A is in V or in W, which means that this is always included in that. So now we have that this is included in that in all cases, and this set is included in that set in all cases. If all the elements of this set are in this set, and all the elements of this set are in this set, then they're the same set. So I guess I should put that over here. So the union of V with W is equal to this. All right, so we've shown that if V and W are affine varieties, then their intersection is an affine variety, and its defining equations are these S plus T polynomial, well, its defining polynomial functions, excuse me, are these S plus T polynomial functions and n variables, x of 1 through x of n. It's just the polynomials that define V and the polynomials that define W here. Those define the variety that results from the intersection of V and W. If V is a variety and W is a variety, V intersected with W is a variety, and this is it. And then we've shown that under the same conditions, if V and W are varieties, we take their union. The union of two affine varieties is another affine variety. And the polynomial functions that define that affine variety just come from taking all the possible products of the polynomials that define this variety and the polynomials that define this variety. Now we've just talked about two varieties here, but if we can do it with two of them, we can do it with three of them. If we can do it with three of them, we can do it with five of them. So that extension yields this fact over here, that finite unions and intersections of affine varieties are affine varieties. Now we've already seen an example of something like this, of this set right here, of an intersection. We didn't say that that's what it was when we were looking at it, but we have seen this before. When we looked at this variety, we had x times z as one polynomial function and x times y as a different, or z times y as a different polynomial function. Well, notice that this is a product. I've got x and y here, and they're both being multiplied by z. So it turns out we can think of this as the union of this variety and this variety. And that makes sense. Think about what this variety is. This is the set of all points where z is equal to 0. And z is equal to 0 in the xy plane. And this is a set of all points where x is equal to 0 and y is equal to 0. And if we're in three-dimensional space, z is free to be anything. So that's the z-axis. X equals 0, y equals 0, z is free. So if I take the product of each of these guys and I multiply it by each of these guys, and it turns out to only be one guy, we get this. I have two polynomials over here and one polynomial over here. I end up with 2 times 1 polynomials over here, which is just 2 polynomials. But notice that this was defined in terms of one variable only. We ended up with this, or one equation only, and we're in three-dimensional space. So it's defined by one equation, and we ended up with something that was two-dimensional. And here we had 2 equations or 2 functions that define this variety. And of course, the functions relate to equations where the functions are equal to 0. For each of these, we decrease the degree by 1, and the dimension of the result is one-dimensional. So this is a one-dimensional object, and this is a two-dimensional object. And when we take the union of them, we have this one-dimensional object combined with this two-dimensional object to give us this variety over here. Okay, so that is it for the finite unions and intersections of varieties. I just want to point out some other interesting questions that we'll answer as we continue to study algebraic geometry. So let's say that we've got S polynomial functions in this polynomial ring. They depend on the variables x of 1 through x of n, and the coefficients of those polynomials lie in a field K. We might be interested in these three questions. First, we're going to ask ourselves about consistency of the equations. The question is it possible to determine whether V is not the empty set? So we might say, does the system of equations f sub 1 through f sub s all equal to 0 have a solution? Now, if we're asking if a system of equations has a solution, another way to say that is this set equal to the empty set? Is it empty? Now, I label this with consistency, or textbook author labels this with consistency as well, because that system of equations may not have a solution, or if that system of equations does not have a solution, excuse me, we call that system of equations an inconsistent system of equations. So for example, the variety xy, or defined by polynomials xy and xy minus 1, is a set of all points xy in some two-dimensional affine space for which xy is equal to 0 and xy minus 1 is equal to 0. Or in other words, we're looking for the set of all points in this two-dimensional affine space for some field K for which xy equals 0 and xy equals 1. Well, that's obviously inconsistent. Xy can't be 0 and 1 at the same time. So this is the empty set. So this is an inconsistent system. We're asking ourselves, is the system consistent or not? Are there any solutions out there? So that's one question that we'll want to answer. Second question is finite. It's about finiteness. Is this set of solutions finite? In other words, do we have a list of solutions in n-dimensional affine space for the system of polynomial equations? When we're asking if the set is finite, we're also, that's the same thing as asking, yeah, is the dimension of this variety equal to 0? So is there a list of points that we can just write down that will just completely describe that affine variety V, the solution of the system of S equations and n unknowns that come from taking these polynomials and setting them equal to 0. And then we're going to say, if this variety is finite, or if the dimension of the variety is 0, so we have just a finite number of points in our solution set, the question is, can we find those solutions explicitly? When we say, can we find the solutions, we mean, can we write them down? Just list all of these solutions that belong to that affine variety. And the third question is a question that we talked about in the last video. It's dealing with the dimension of V. can we determine the dimension of V? Like we talked about last time, if we have m equations and n unknowns, we might expect the dimension of V to be m minus n, or n minus m. But we know that that's not always the case. And the fact that that's not always the case has something to do with the fact that if equations are dependent on each other, if they're dependent equations, so they're just different ways of perhaps saying the exact same thing, well, having basically the same equation on your list twice, that shouldn't reduce the dimension of V by anything, that you happen to have it twice instead of having it once. So this really has something to do with independence. It also has something to do, it has something to do with the independence of those equations, but that notion of independence is a little different in algebraic geometry than it is in other classes. Also, we talked about the fact that if I'm in three-dimensional space, you might expect the dimension to go down by 2. In this example, I've got 2 equations and 3 unknowns. You might expect something of dimension 1, but we have something of dimension 1 and something of a dimension 2. And that's related to the fact that we have that union there. So that might be related as well. We have to be careful about the field that we're interested in. If we are talking about the field of real numbers, we get to draw all these pretty pictures and it makes it nice and easy. But if we're talking about the field of complex numbers, we can come up with different results. There's really a lot of algebra to talk about here. And I'm not talking about algebraic manipulation in the sense of like high school algebra, but I'm talking about abstract algebra that's necessary in order to answer this question. Okay, so that is the end of our discussion of finite unions and intersections of affine varieties and related questions. In the next video, we'll talk about just a very simple application of affine varieties to robotics. It's a super simple example. It almost doesn't deserve its own video, but I wanted to include it for completeness of my notes over section 1.2. And then we'll go on to section 1.3, which is about parameterizations of affine varieties.